January 5th, 1943, 11:40 a.m., the Solomon Islands. Aboard the light cruiser USS Helena, the tropical air is thick with tension and the smell of fuel oil. The ship is a battered veteran of brutal night engagements against the Japanese Imperial Navy, but today the threat comes from above. The ship's radar operators spot 4 distant contacts closing in fast, identifying them as Japanese Aichi D-3A dive bombers, known to the Allies as Vols. As the enemy aircraft begin their attack run, the Helena's 5-inch guns elevate and track the incoming swarm. Deep in the magazine's below deck, sailors are loading a brand new type of ammunition, something so highly classified that its true nature is known to only a handful of officers on board. It is officially designated the Mark 32, but informally, the scientists who built it call it the VT Fuze. As the first Japanese dive bomber enters firing range, the massive deck guns roar to life, sending shockwaves across the water. The gunners are not aiming for a direct hit, nor have they set a mechanical timer based on a frantic, desperate altitude calculation. They just need to get the shells somewhat close to the target. The projectile arcs through the Pacific sky at blistering speed. When it passes within 70 feet of the enemy plane, a tiny, fragile radio transmitter hidden inside the nose of the bullet detects the aircraft's reflection. Faster than a human eye can blink, an electrical circuit closes, a detonator fires, and the shell erupts in a deadly, expanding cloud of jagged steel shrapnel. The Japanese dive bomber is instantly shredded, its wings torn away as it spirals down into the sea in a spectacular ball of fire. On the deck of the USS Helena, the crew erupts into cheers, stunned by the sudden, violent efficiency of their weapons. In a single stroke, the terrifying mathematical puzzle of anti-aircraft warfare has been solved, and the balance of power in the skies has changed forever. To understand the sheer miracle of the technology inside that shell, one must look back to the dark days of the early war. September 7, 1940, 5 p.m., London, England. The skies over the British capital are darkened by the first massive waves of the Luftwaffe's bombing campaign, an era of terror that will become known as the Blitz. On the ground, British anti-aircraft crews work frantically, feeding millions of artillery shells into their heavy guns and firing them into the night sky. The noise is deafening, and the sky is filled with the flashes of exploding ordnance, but the results are devastatingly poor. Firing at airplanes from the ground using the technology of 1940 is an exercise in futility. The anti-aircraft shells of the time rely on 2 basic types of fuses. The first is a simple contact fuses, which requires the artillery shell to physically strike the enemy aircraft to detonate. Hitting a fast-moving bomber flying at high altitude with a single artillery shell is roughly equivalent to shooting a flying bird with a rifle while wearing a blindfold. It is virtually impossible. The second option is the time fuse. This requires gunners to calculate the exact altitude, speed, and trajectory of the incoming bomber, estimate how long the shell will take to reach that specific point in 3-dimensional space, and then manually twist a dial on the nose of the shell to set a mechanical clock. The shell is then fired, and the clock ticks down. If the math is absolutely flawless, the shell explodes in the middle of the bomber formation, destroying the aircraft with shrapnel. But airplanes do not fly in straight lines at constant speeds when they are being shot at. A bomber flying at 300 miles per hour moves hundreds of feet in the mere seconds it takes a shell to travel from the ground to the sky. A miscalculation of a fraction of a second, or an error in altitude estimation of just 50 feet, means the shell explodes harmlessly in empty space. The statistics are grim. During the Blitz, it takes an average of 20,000 artillery rounds fired to bring down a single German aircraft. The expenditure of ammunition is astronomical. The barrel wear on the guns is severe, and the falling shrapnel from missed shots causes immense damage to the city below. The British military realizes that what they need is a shell that acts like a proximity mine, something that knows when it is near a target and detonates automatically. The concept is brilliantly simple, but the engineering required to make it a reality borders on science fiction. The British had theorized about proximity fuses before the war, envisioning acoustic sensors, photoelectric cells, or tiny radar sets. But the sheer violence of being fired from a cannon makes putting delicate electronics inside an artillery shell seem physically impossible. Realizing their manufacturing base is under constant bombardment, the British passed their preliminary research to the United States. In Washington, the National Defense Research Committee, led by the visionary Vannevar Bush, assigns the impossible task to a special division known as Section T. The group is headquartered at the Department of Terrestrial Magnetism and later moves to the Applied Physics Laboratory at Johns Hopkins University. Section T is placed under the command of Merle Tuve, a brilliant and fiercely determined physicist from North Dakota. Tuve is a pragmatic man who believes in aggressive trial and error. He understands that to build a proximity fuse based on radar, his team must somehow shrink a continuous wave radar transmitter and receiver down to the size of a milk bottle. But size is not the primary obstacle. The true nightmare is the physical environment the electronics must survive. When a standard 5-inch anti-aircraft gun is fired, the shell undergoes an acceleration of 20,000 times the force of gravity. To put this in perspective, imagine a 150-pound human being subjected to 20,000 Gs. For a brief, violent millisecond, their body weight would increase to 3 million pounds. The sheer concussive shock of the gunpowder explosion is enough to flatten solid blocks of metal, but the forward acceleration is only half the problem. To keep an artillery shell flying straight and true, the barrel of the gun is heavily rifled, forcing the shell to spin rapidly as it travels to the air. By the time the shell exits the muzzle, it is spinning at an agonizing 30,000 revolutions per minute. This generates massive centrifugal force, threatening to rip any internal components outward toward the casing. Inside this apocalyptic environment of shock and spin, Merle Tuve and his team are trying to place delicate glass vacuum tubes, fragile wire filaments, and sensitive electrical components. Vacuum tubes in 1940 are comparable to household light bulbs. They are brittle, sensitive to the slightest vibration, and break easily if dropped on a table. The idea of firing them out of a cannon is considered utter madness by most conventional engineers. Tuve refuses to accept that it cannot be done. He sets up a brutal testing regimen. His team places standard glass vacuum tubes into lead blocks and drops them from the roof of a high-rise building onto a concrete driveway. Unsurprisingly, the tubes shatter into powder. They begin experimenting with different ways to cushion the blow, encasing the glass tubes in various compounds like rubber, beeswax, and synthetic plastics. Eventually, they discovered that if the tubes are suspended in a specific type of microcrystalline wax and then encased in hard plastic, the force of an impact is distributed evenly across the glass surface, preventing it from shattering. But dropping tubes from a roof is not the same as firing them from a gun. The team moves their operations to a muddy farm field in Maryland, where they set up a smooth-bore 37mm cannon. They load their reinforced vacuum tubes into custom projectiles and fire them straight up into the air. They then wander through the fields, digging the shells out of the dirt, cracking them open, and hooking the tubes up to electrical testers to see if the filaments survived. Most of the time, the filaments snap. The team turns to commercial manufacturing partners, specifically Sylvania Electric Products, to help them design ruggedized miniature tubes. These new tubes are based on the tiny components used in the latest hearing aids, but heavily reinforced. The glass envelopes are thickened, the internal wire filaments are shortened to reduce vibration, and the entire assembly is rigorously tested. Gradually, the survival rate of the vacuum tubes fired from the test cannons climbs from 0% to 20%, then 50%, and finally an acceptable rate of over 80%. However, the glass vacuum tubes are only one piece of the puzzle. The fuse requires a power source, A radar transmitter cannot function without electricity, and the standard dry cell battery poses an insurmountable logistical problem. Dry cell batteries degrade over time, a phenomenon known as shelf life. If the military ships millions of these fuses to the tropical heat of the Pacific Theater, standard dry batteries will drain and corrode within weeks, rendering the proximity fuses completely useless. The military requires a battery that can sit in the belly of a warship or in an ammunition dump for years without losing a fraction of a volt, and then deliver a powerful surge of electricity exactly when needed. The scientists of Section T invent a solution so elegant and reliable that it remains a masterpiece of mechanical engineering. They create the reserve battery. The design consists of thin circular plates of carbon and zinc stacked together, but kept completely dry. The electrolyte fluid, specifically liquid chromic acid, is sealed tightly inside a tiny, delicate glass ampoule sitting in the center of the battery stack. When the shell sits in storage, the battery is dead, completely inert. But the moment the artillery gun fires, the massive shock of the 20,000 G acceleration shatters the glass ampoule. In the next millisecond, the 30,000 revolution per minute spin of the shell forces the corrosive liquid outward through the stack of carbon and zinc plates. Centrifugal force instantly coats the plates with the acid, triggering the chemical reaction. In less than a tenth of a second after leaving the gun barrel, the battery springs to life, delivering a steady electrical current to power the radar. With the power and the vacuum tube solved, the team must confront an equally terrifying issue. The fuse must be completely safe to handle on the deck of the ship. If a proximity fuse arms itself too early, the radar might detect the ship's own mast, or an adjacent friendly vessel, or even the water itself, and detonate the shell inches from the gun barrel, killing the crew. The safety mechanisms must be foolproof. The engineers devise a brilliant series of interlocking mechanical switches that rely entirely on the physical forces of being fired. The primary safety is a mercury switch. Inside the nose cone is a small chamber containing liquid mercury, held in place by a porous barrier. Under normal handling conditions, the mercury stays in a safe position, keeping the firing circuit completely open. But when the gun is fired, the extreme centrifugal force of the spinning shell forces the mercury through the porous barrier and into a second chamber. It takes exactly half a second of continuous, violent spinning for enough mercury to migrate and bridge an electrical contact. This half-second delay ensures the shell has safely traveled hundreds of yards away from the ship before the electrical circuit is completed. An additional safety mechanism uses small metal reeds held in place by a tiny drop of solder. As the shell spins, the friction of the air over the nose cone heats the metal, melting the solder and releasing the reeds, fully arming the firing circuit. Only when the shell is far away from the ship, fully powered and actively transmitting its radio wave, is it ready to kill. As the shell approaches an enemy aircraft, the continuous radio waves emitted by the tiny antenna in the nose bounce off the metal skin of the target. The reflected waves return to the shell. Because the shell is moving rapidly toward the target, the returning waves are compressed, shifting their frequency. This is known as the Doppler effect. The tiny circuit inside the fuse mixes the transmitted frequency with the received frequency, creating a low-frequency beat note. As the shell gets closer, the amplitude of this beat note increases. When the shell is within roughly 70 feet of the aircraft, the signal becomes strong enough to trigger a thyrotron tube, which acts as an electronic switch. The thyrotron suddenly releases a surge of electricity from a storage capacitor directly into a small wire embedded in an explosive squib. The wire instantly vaporizes from the heat, detonating the squib, which in turn sets off a booster charge, which violently explodes the massive main charge of the artillery shell. From the moment the radio waves detect the plane to the moment the shell explodes, less than a millisecond passes. The aircraft does not have to be directly in the path of the bullet. It merely has to enter an invisible 70-foot sphere of death. By mid-1942, the basic design is finalized. The American military recognizes the world-altering potential of the weapon and immediately classifies the project at the highest level of secrecy, rivaling only the Manhattan Project, which is simultaneously building the atomic bomb. No one can know that radios are being put inside bullets. The military assigns the weapon the deliberately boring and misleading name, Variable Time Fuze, or VT Fuze. The hope is that if enemy intelligence intercepts communications about it, they will simply assume the Americans have designed a slightly better mechanical timer. Production must be scaled up to astronomical levels. Sylvania, RCA, Crossley, and Eastman Kodak are mobilized. Entire factories are converted to manufacture the tiny components. Because of the extreme secrecy, the assembly process is compartmentalized. Tens of thousands of factory workers, the vast majority of them women, are trained to assemble specific parts of the fuse, using microscopes and tweezers to handle wires as thin as a human hair. They are told absolutely nothing about the final product. A worker might spend 12 hours a day soldering 3 wires to a tiny glass tube, completely unaware that she is building the radar brain of an anti-aircraft shell. By the end of the war, over 22 million VT fuses will be manufactured, a staggering logistical triumph. Before it can be trusted in combat, the Navy demands a live fire demonstration. On August 12, 1942, 10 a.m., the light cruiser USS Cleveland steams through the waters of the Chesapeake Bay. The Navy launches 3 radio-controlled target drones to simulate an enemy attack run. The crew of the Cleveland has been issued a small batch of the new, highly classified Mark 32 VT fuses. The first drone buzzes over the horizon. The Cleveland's guns track the target and fire. The very first salvo, consisting of just a few shells, intercepts the drone perfectly. The fuses detonate with terrifying precision, blowing the target into splinters. The high-ranking naval officers watching the test are absolutely speechless. The second drone is launched. It is destroyed just as easily. The third drone is targeted, and the gunners purposely aim slightly off-center to test the proximity limit. The shell passes near the drone, the radio waves detect the wood and metal structure, and the shell explodes, bringing down the third target. The test is a phenomenal success. The kill rate is hundreds of % higher than the best mechanical time fuses in the inventory. The Navy immediately orders the fuses to be fast-tracked to the Pacific Theater. However, a strict operational order accompanies the first shipments. The Joint Chiefs of Staff issue a terrifying directive. The VT Fuze is absolutely forbidden to be fired over land. If a shell is fired at a plane and the fuse fails to detonate, a dud shell will fall back to Earth. If it falls into the ocean, it sinks into the abyss, safely hiding the secret forever. But if a dud falls on enemy-held land, the German or Japanese military will recover it. Their scientists will crack open the casing, recognize the vacuum tubes and the radar antenna, and instantly realize what the Americans have done. Armed with this knowledge, they could quickly develop electronic countermeasures to jam the radio signals, rendering millions of fuses useless. Worse, they could reverse engineer the technology and begin using it against Allied bombers, turning the skies over Europe into an impenetrable wall of flak that would decimate the American 8th Air Force and the British Bomber Command. The stakes are too high. Admiral William Halsey, commanding operations in the South Pacific, is given strict instructions to ensure his ships only fire the specialized ammunition while operating over deep water. This brings the story back to that fateful morning on January 5, 1943, 11:40 a.m. The USS Helena's successful engagement of the Japanese dive bomber marks the first confirmed combat kill using the VT Fuze. The impact on naval warfare is immediate and catastrophic for the Japanese Air Forces. Throughout 1944 and 1944, as the American island-hopping campaign pushes relentlessly across the Pacific toward the Japanese home islands, the VT Fuze becomes the ultimate shield for the fleet. The air battles culminate in the massive engagements of the Philippine Sea, often referred to as the Marianas Turkey Shoot. American fighter planes decimate the poorly trained Japanese aviators, but those enemy planes that manage to break through the fighter screen run headlong into a wall of proximity-fused artillery fire. The traditional tactic of flying evasive maneuvers through anti-aircraft fire no longer works. It does not matter how radically a pilot jinks or rolls. If the plane flies anywhere near the American shells, it is blown out of the sky. By late 1944, out of pure desperation, the Japanese resort to the terrifying tactic of the kamikaze. Realizing that conventional bombing attacks are failing due to the devastating effectiveness of American air defenses, Japanese pilots are ordered to load their planes with explosives and fly them directly into the decks of American warships. The Battle of Leyte Gulf sees the first organized kamikaze attacks. October 25, 1944, 2:15 p.m. The skies over the Philippine Sea are filled with the smoke of burning ships and the frantic chatter of radio communications. Japanese Zeros and Vals, stripped of excess weight, dive vertically toward aircraft carriers and destroyers. It is an act of sheer psychological terror, and conventional time fuses are completely useless against a plane plunging in a vertical death dive. The calculations change too rapidly to set a mechanical timer, but the VT Fuse does not care about speed, angle, or altitude. The American gunners simply point their 5-inch guns along the flight path of the diving kamikaze and fire as rapidly as the autoloaders can cycle. The sky is filled with black puffs of smoke as the proximity fuses detect the plunging aircraft and detonate instantly. The resulting shrapnel walls literally shred the kamikazes in midair, causing the planes to disintegrate before they can hit the ships. While some kamikazes inevitably slip through and cause horrific damage, the survival of the American fleet is largely credited to the VT Fuse. Without the Proximity Fuze, the casualty rate among American sailors during the kamikaze campaigns of Okinawa and Leyte Gulf would have been astronomically higher, potentially threatening the success of the entire Pacific campaign. While the Navy utilizes the weapon to devastating effect in the Pacific, a new and desperate crisis is unfolding in Europe. June 13, 1944. Shortly after the D-Day landings in Normandy, the citizens of London hear a strange, terrifying sound echoing through the night sky. It is a harsh, sputtering pulse, much like a badly tuned motorcycle engine. It is the V-1 flying bomb, Hitler's vengeance weapon. The V-1 is an early cruise missile, an unmanned drone packed with high explosives. It flies at low altitudes, around 2,000 to 3,000 feet, and travels at roughly 400 miles per hour. Because it has no pilot, it flies in a dead straight line. On paper, it seems like an easy target for anti-aircraft guns, but its speed and extremely low altitude make it virtually impossible to shoot down with conventional time fuses. By the time a gunner spots the buzz bomb, tracks its altitude, sets the timer on the shell, and fires, the missile has already flown miles away. For weeks, the V-1s rained down on London, causing massive civilian casualties and threatening to paralyze the British war effort just as the Allies are fighting their way through France. Prime Minister Winston Churchill pleads with the United States to release the highly restricted VT fuses for use on land. He argues that the threat to London and to the vital supply ports in southern England is far greater than the risk of a dud falling into German hands. The American military leadership, deeply conflicted, finally agrees to lift the restriction, but only under highly controlled circumstances. Anti-aircraft batteries equipped with VT fuses are moved out of London and relocated entirely to the southern coast of England. This strategic redeployment is designed to ensure that any fuses fired at incoming V-1s will either hit the missile or fall into the English Channel, minimizing the risk of a dud landing on dry soil. The results are nothing short of miraculous. During the first weeks of the V-1 attacks using conventional ammunition, British and American gunners were successfully shooting down barely 20% of the incoming buzz bombs. The introduction of the VT Fuse fundamentally alters the math of the engagement. By August of 1944, The coastal batteries are destroying over 70% of the V-1s before they even cross the coastline. In one phenomenal single-day action, anti-aircraft crews shoot down 68 V-1 flying bombs out of 72 that enter their sector. The terrifying menace of the buzz bomb is effectively neutralized, largely thanks to the tiny radar sets hidden inside the artillery shells. Later in the fall of 1944, the crisis shifts again. The Allied armies have captured the vital deep-water port of Antwerp in Belgium. This port is absolutely crucial to supplying the massive Allied war machine as it pushes toward the German border. Recognizing the strategic importance of Antwerp, Adolf Hitler orders the V-1 and the new supersonic V-2 rockets to be redirected at the Belgian city. A massive anti-aircraft defense grid is established around the city, codenamed Antwerp X. Once again, the VT Fuze is authorized for deployment, though the risk of duds falling into German territory is increasing as the front lines shift. The American gunners in the Antwerp X defense ring use the Proximity Fuze with devastating efficiency, shooting down thousands of V-1 missiles and saving the port from complete destruction. The flow of vital supplies to the front continues uninterrupted, keeping the pressure on the collapsing German army. But the most dramatic and controversial use of the VT Fuze is yet to come. By late 1944, the ban on using the Fuze over land is increasingly seen as a hindrance by field commanders. General George S. Patton, commanding the U.S. Third Army, is acutely aware of the tactical advantages of airburst artillery. When fighting infantry in open terrain or entrenched in foxholes, standard contact fuses are incredibly inefficient. When a traditional high-explosive shell hits muddy ground or deep snow, the soft earth absorbs a massive amount of the explosive energy and shrapnel, directing the blast straight upward in a column of dirt. Infantrymen hiding in slit trenches are largely protected unless the shell lands directly inside the hole. Field commanders had previously tried using time fuses to create airbursts, attempting to detonate the shells 50 feet above the ground to rain shrapnel down into the trenches. But setting time fuses for ground targets requires complex mathematics and perfect observation, which is nearly impossible in the chaos of battle, especially at night or in thick fog. If the timer is off by a fraction of a second, the shell either explodes harmlessly high in the air or buries itself in the mud before detonating. December 16, 1944. 5:30 a.m. The Ardennes Forest. The German army launches a massive surprise counteroffensive that will become known as the Battle of the Bulge. Hundreds of thousands of German infantrymen and tanks pour through the snow-covered forests, smashing into thinly held American lines. The weather is atrocious. Heavy fog and blinding snowstorms ground Allied air support, leaving the outgunned American infantry desperately fighting for survival. In Washington, the agonizing decision is finally made. On December 18th, the absolute restriction is lifted. The VT Fuze is authorized for field artillery use against German ground troops. Urgent messages are sent to artillery battalions across the frozen front lines. Crates of the secret ammunition, marked with a distinctive green painted nose, are cracked open and distributed to the howitzer crews. The impact of the VT Fuze on the advancing German infantry is immediate, horrific, and absolute. The American howitzers elevate and fire into the dense fog, relying on map coordinates. The shells arc high over the Ardennes forest and begin their descent. But instead of burying themselves in the deep snow, the miniature radar sets in the nose cones detect the approaching frozen earth. Exactly 50 feet above the ground, the radio waves trigger the detonator. The shells explode in brilliant flashes of fire against the gray winter sky. The result is a lethal, conical shower of jagged steel shrapnel blasting straight downward at supersonic speed. There is absolutely no defense against it. Trenches, foxholes, and wooden bunkers offer zero protection against fragments raining from directly above. Entire formations of German infantry, massing in the forests for attacks, are decimated in minutes. The psychological tear inflicted on the enemy troops is profound. They cannot hear the shells coming in time. They cannot hide from the blast, and the explosions seem to happen magically in midair regardless of the terrain. General George S. Patton will later write to the War Department explicitly stating that the new Fuzes required a complete revision of the tactics of land warfare. He notes that the combination of the Proximity Fuze and massed artillery fire is the most devastating killing mechanism he has ever witnessed on a battlefield, bluntly crediting it with saving countless American lives and breaking the back of the German offensive. The devastating airbursts shatter the morale of the advancing German units, turning the snowy forests of the Ardennes into an inescapable slaughterhouse and halting the momentum of Hitler's final gamble in the West. As the war grinds to a close in the spring and summer of 1945, the true scale of the achievement becomes clear. The VT Fuzes stands as a towering testament to the power of rapid, relentless scientific innovation. Merle Tuve and the eccentric brilliant engineers of Section T took a theoretical concept that the world deemed physically impossible and through brute force testing and sheer willpower, turned it into one of the most decisive weapons of the 20th century. They solved the nightmare of firing fragile glass vacuum tubes out of cannons at 20,000 Gs. They invented a battery that could lie dormant for years and wake up in a millisecond. They manufactured millions of intricate, microscopic circuits using a completely compartmentalized civilian workforce that never knew the immense value of their daily labor. The military kept the secret perfectly. Neither the Germans nor the Japanese ever realized that the devastating accuracy of American artillery was driven by tiny radios hidden inside the bullets. The Proximity Fuze directly saved the Allied fleet from the Kamikaze Menace in the Pacific, shielded London from the terror of the buzz bombs, and shattered the last great German offensive in the snows of Europe. Alongside radar and the atomic bomb, the VT Fuze is universally recognized by military historians as one of the three most significant technological breakthroughs of the Second World War. The technology pioneered in those muddy test fields in Maryland laid the absolute foundation for the modern era of guided missiles, smart munitions, and electronic warfare. Every radar-guided missile, every proximity warhead, and every modern anti-aircraft system owes its existence to the men and women who dared to build a radio small enough and tough enough to be fired out of a gun.